All I am is a man. I want the world in my hands. I hate the beach.
Look up at the night sky. It's a breathtaking sight, filled with countless twinkling stars. Each star is a distant sun, a giant ball of burning gas. They seem eternal, but stars have a life cycle just like us. They are born, they shine brightly, and eventually, they die. Their stories are tales of immense energy, incredible transformations, and cosmic drama. For centuries, humans have gazed at the stars and wondered about their mysteries. What are they made of? How do they shine so brightly, and what happens when they die? Today, thanks to the power of science, we can begin to answer these questions. We can trace the life cycle of stars from their birth in vast clouds of gas and dust to their dramatic deaths. The story of a star's life is a story of gravity. Gravity pulls matter together, squeezing it tighter and tighter. This squeezing generates heat and pressure, eventually igniting the nuclear furnace at a star's core. The life and death of a star are a delicate dance between the inward pull of gravity and the outward push of energy. Join me now as we journey across the vast expanse of space and time to explore the fascinating life cycle of stars. Stars are born in vast, cold clouds of gas and dust scattered throughout galaxies. These clouds, called nebulae, are like cosmic nurseries, providing the raw materials for star formation. Gravity is the driving force behind star birth. Within a nebula, gravity slowly pulls gas and dust particles towards each other. As more and more matter clumps together, the cloud's core becomes denser and hotter. This dense, hot core is called a protostar. The protostar continues to grow, pulling in more and more material from the surrounding nebula. As it grows, its core gets even hotter and denser. Eventually, the temperature and pressure at the core becomes so intense that nuclear fusion begins. Nuclear fusion is the process where hydrogen atoms combine to form helium, releasing a tremendous amount of energy. This energy creates an outward pressure that balances the inward pull of gravity. The protostar has now become a star. Once nuclear fusion begins in a star's core, it enters a long, stable period called the main sequence. This is the longest stage in a star's life, and our own sun is currently in its main sequence. During the main sequence, a star fuses hydrogen into helium in its core, releasing a constant stream of energy in the form of light and heat. The balance between gravity pulling inward and energy pushing outward keeps the star stable. The length of a star's main sequence lifetime depends on its mass. Massive stars are hotter and brighter, burning through their hydrogen fuel much faster than smaller stars. Our sun, a relatively small star, will spend about 10 billion years on the main sequence. Massive stars, on the other hand, may only spend a few million years in this stage. Their immense gravity forces them to burn their fuel at a much faster rate. This intense energy output makes them incredibly luminous, but it also means they live fast and die young. Section 4. The Twilight Years, Giants and Supergiants. Eventually every star runs out of hydrogen fuel in its core. When this happens, the outward pressure from nuclear fusion weakens, and gravity takes over. The star's core begins to contract, becoming even hotter and denser. As the core contracts, the outer layers of the star expand outward, causing it to swell up to an enormous size. The star's surface cools, giving it a reddish hue. At this stage, the star has become a red giant, or, if it was initially very massive, a red supergiant. Red giants and supergiants are truly colossal objects, hundreds or even thousands of times larger than our sun. If our sun were to become a red giant, it would engulf the orbits of Mercury, Venus, and possibly even Earth. Inside a red giant or supergiant, the core continues to contract and heat up. Eventually, the temperature and pressure become high enough to ignite the fusion of helium into heavier elements like carbon and oxygen. This fusion process releases even more energy, further extending the star's life, but only for a short while. Section 5. Stellar Demise, from white dwarfs to black holes. The final stages of a star's life depend on its mass. Smaller stars like our sun will eventually shed their outer layers into space, forming beautiful, glowing clouds of gas called planetary nebulae. At the center of a planetary nebula lies the star's exposed core, a small, dense object called a white dwarf. White dwarfs no longer produce energy through fusion. Instead, they slowly cool and fade over billions of years. Massive stars, however, meet a far more dramatic end. When a massive star runs out of fuel, its core collapses catastrophically under its own gravity. This collapse triggers a supernova, a colossal explosion that blasts the star's outer layers into space. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. The remnants of a supernova explosion can form two incredibly dense objects: neutron stars and black holes. Neutron stars are incredibly dense objects, packing the mass of our sun into a sphere just a few miles across. Black holes are even more extreme, with gravity so strong that nothing, not even light, can escape their grasp. The death of a star, while marking the end of one journey, paves the way for new beginnings. The material ejected during supernova explosions, enriched with heavy elements forged in the star's core, eventually becomes part of new nebulae. Within these nebulae, gravity will once again work its magic, collapsing gas and dust to form new stars, planets, and perhaps even life. And so, the cycle continues. The death of stars gives birth to new generations, perpetuating the cosmic dance of creation and destruction across the vast canvas of space and time.